P4BID is a joint work with Loris Tantoni from University of Wisconsin-Madison and Justin Su from Cornell University. In the past, network switches have mostly been fixed function devices, but recently there has been a shifting trend towards making them more programmable and customizable. In wake of this, P4 programming language has come across as one of the go-to choice for programming these switches. With the flexibility to program your switches, we have enabled the implementation of in-network devices, in-network implementation of several otherwise data center functions like key value stores, and load balancers in favor of performance benefits. The P4 programming language provides you language constructs to customize different parts of packet processing pipeline, which can include three important things: the parser, the main packet processing pipeline itself, and the deparser. And for the sake of this talk, we'll be focusing on the main packet processing pipeline. Well, everything's good. You have the capability to program your switches, but this opens a new challenge. Now, you will have programming errors that can lead to incorrect network behaviors because these switches are performed incorrectly. And this work focuses on one class of security vulnerabilities that arise mostly because of illicit information flow happening in between the packet headers during your custom packet processing pipelines. To understand what it means for information to leak between packets, consider a network packet having fields labeled private and some of them being the public fields. And now you try to process this packet by some program written on a switch, and we assume that this program is trying to write to a public field with some private data. When this packet comes out after being processed, it would have its public fields polluted by some private information. And this kind of scenario is what we consider to be information leak. To motivate this problem, let's consider a gateway switch that is interfacing a public network and a private data center. The data center itself is running two applications, namely foo and bar, where foo happens to be a latency-sensitive application. So we want our programmable switch to implement resource-aware forwarding logic, where you would want that packets for foo have their priorities increased, while bar's packet are sent out at lower priority than foo's packet. Now, to implement this, a network operator comes up with a custom packet header definition that includes fields like application ID, destination IP, and priority. Consider a possible implementation of this logic where you are trying to increase the priority and setting it based on the application ID. Now, you can have an attacker, and the attacker would observe that foo's packets have their priorities increased. Well, that's fine. Bar's packets do not have their priorities increased. That's also fine. But now, this attacker can misuse this information to do notorious stuff. For instance, it can try to spoof a bar's packet and make it appear that it's foo's packet. What this would lead is sending out a packet that was initially meant to be bar's packet in disguise of being foo's packet. Why? Because you didn't update the destination IP, but you're sending this thing out at increased priority. In this work, we focus on detecting and preventing these kind of information leak by coming up with our tool P4BID, which is a type system based on information flow control. We try to implement P4BID on top of P4's reference compiler as a type checker. And finally, we encode networking properties into IFC properties to showcase the expressivity of our type system. To understand what are the main ideas of the classical IFC, I'll first review some of the bits from it. Well, you first start off by having a security lattice. This lattice is going to give you security labels that you'll see how we'll use later on. In this case, we are using a 2-point lattice for simplicity, having fields labeled low and high. Now, you're going to label your variables in the program using the labels provided by your security lattice. In this case, we can consider that the application ID field that we were talking about in our previous example can be labeled as a high field, meaning that it is an untrusted or manipulable field. Similarly, we can label fields like the destination IP and priority as low or trusted fields. Trusted meaning that it would be non-manipulable. Lastly, we come up with the security types, which are pair types, composed of your base type and a security label. Now consider you have your application ID having the following type. What it means is application ID will be an untrusted field of the integer type. Now we'll try to see what it means for what are the guarantees well-typed program provides when it type checks according to an IFC type system. Suppose this program is well-typed, and now when you try to run it on an input state which is having some high variables and low variables, and you evaluate this program on that input, you get some output. Everything's nice so far. But now let's try to change the input and change only the value of its high variables. If the program was well-typed according to your IFC type system, it would guarantee that when you evaluate this program on the input at the bottom, it will still try to have the same value in the low variable as the first scenario. Lifting up these classical ideas from IFC had their own set of challenges when we were trying to do them for P4. This was because the language provided several rich language constructs. To understand what kind of language constructs are we talking about, let's consider an implementation of the running example that we just discussed, but in actual P4. So we'll be trying to increase the priority based on the application ID. Firstly, we'll come up with an action. An action happens to be function in the conventional sense. So here, the set priority action would take in the new priority argument, and then it will try to increase or like to set the value into the header.priority field. Next, we'll have a table. Tables will have keys and actions. Keys are going to be your packet header fields. Operationally, a table would map values of your keys into the actions that need to be invoked. But there is a catch here. The entries in the table are not going to be provided with the P4 program itself, but rather it would be installed at runtime by an external network controller. And finally, we have the statement that is the entry point into this program, and there we are just trying to invoke the app to priority table that we just defined. So in this program, you would invoke the table. The table would check the input field header.app ID from your packet header and try to invoke the set priority action with appropriate argument. The language features provided in P4 increase the sources of information leak, but since tables happen to be the most unusual language features, for the rest of this talk, we are going to focus on security vulnerabilities that involve tables. A table that matches on high security key and then tries to invoke an action that would write to a low security variable is going to be a source of information leak. Now, to understand why, we can semantically unfold the table into a conditional block where you would be branching on the high variable, which happens to be your key that the table defined. And then you would be invoking an action that would be writing to a low variable. Recall this is one of the classical implicit leak scenario presented in classical IFC. To understand how this kind of bug could look like in P4 program and to see that our implementation was actually having this bug, we'll revisit the running example. To do so, first we would try to label security types for our packet headers. This would look like something like this, where you have labeled your application ID with untrusted security label and destination IP with trusted security label. And the header type itself would be a record type of all these packet header fields. Once you have a program that had the types that we just saw before, and you consider the table that we were looking at, which was having a high security or an untrusted key, it's going to pose an information leak. Why? Because you try to unfold it into this conditional block. What's happening in the conditional block is that you're branching on an untrusted variable and then trying to set value to a trusted variable. This is why the table that we were considering was having leak and was not secure. To detect these kind of security leaks, we present a type system called P4BID, and a well-typed statement or a program in our typing system would have this kind of a simplified typing judgment, where gamma happens to be the initial typing context, and gamma prime is the final typing context, having your variables with their security types after the statement has evaluated. And PC is a security label derived from the lattice we just defined, and it says that this statement is not going to have writes happening to any variables below PC. In the paper, we also show the non-interference theorem for a type system, which means that if you have a well-typed statement, then it's going to be non-interfering, meaning we wouldn't have information flow happening from high to low variables. To see what this looks like in case of our buggy table implementation, we would have the invocation to the table. This judgment would not be provable, and to see why, it is because when you invoke this table, you're trying to set the value of a trusted variable by depending on an untrusted variable, that is the value of the application ID field. However, the fix is simple. You just replace the untrusted field with the trusted label, and then all of a sudden, your program is well-typed, meaning it wouldn't have any security leaks, and it is going to be any information leak, and it's going to be secure. Why? Because now your program is having assignments to trusted variables, which only depend on trusted variables, and it's all good. To summarize our work, P4BID is implemented on top of the reference P4 compiler, and it would take in a P4 program and flag the IFC leaks based on these security types that you had annotated in your program. To see more about the full type system and the intricacies of the non-interference theorem and several interesting applications where we're trying to encode network scenarios into IFC, do check out our paper. This work has left some open questions around dealing with information leak in more advanced P4 programs, like the ones having recirculating packets, or those involving inter-packet leaks because you've been maintaining some state in your switch. Thanks, and we're open for questions.
Thanks, the speaker. Yeah, and we have 5 minutes for questions. If you have any questions, please come to the stage and grab the mic. Any questions from the audience? Okay. Yeah, could you please come to the...
So this is seems like a nice application of information flow control. You showed the labels you have here that you showed were just trusted and untrusted. And I'm curious if that's really enough to capture the kind of security requirements of real systems. And do you it seems like you're thinking more about the integrity side since you're doing trusted and untrusted, but obviously there's confidentiality issues in networks too. So if you could comment on that.
Thanks for your question. Yeah, so for the sake of simplicity over here in this example, we were just considering security levels which could be encoded concretely as trusted and untrusted. But our paper talks about several interesting scenarios where you change the lattice, make it more fancier, and you have more than just the notion of trusted and untrusted. And then you can try to encode properties like isolation between two different P4 programs. I can take this offline to describe more about how we are doing it, but this is just a simple scenario. As the lattice gets fancier, you get fancier properties that can be encoded.
Hi, very nice work. My question is about input packets. So it sounds like some fields in the input packet are marked as private or trusted and some are not. I'm wondering how you just determine that and whether the user has to annotate that or whether there's some inherent property of network programs that tells you that. Thank you.
Thanks again. That's an interesting question. And the way we are trying to label these packet header fields is based on we require the programmer to label them based on the scenario or the natural language model that they have in their minds about what scenario are we trying to encode in this program. So the semantics of these labels are, again, as I mentioned, would depend upon the context or the scenario you're considering. And the programmer needs to annotate it based on how they perceive the fields would be interacting or what their intended application is.
Hello. How do you hope to see your work adopted by the P4 community?
I'm sorry, could you just repeat your question?
How do you hope to see your work adopted by the P4 community?
Yes, so is your question that I hope this work to be adopted?
How so?
How also? All right, so for starters, yes, definitely. We do perceive and that this work has a lot of weight to be adopted by the P4 community because it's a forward-seeking and forward-seeing work where you're trying to figure out that these problems would become more universal as P4 gets adopted widely and you're moving more towards the programmable switches. And for starters, we hope that our efforts in implementing this on top of the reference compiler, which is sort of a backbone for a lot of P4 implementations, for compiling a lot of P4 implementations, this is a right step in that direction.
Thank you so much. Thank you so much for the talk. I have a generic question. I'm not a P4 expert, but you are. So do you see a reason for hardware accelerators for P4? That's my question.
Okay, if I understand it correctly, you mean that P4 as a language to program your hardware accelerator?
No, so essentially have as a dedicated hardware just to process all the P4 requests on the switch, for example, right? So
like you want to run your P4 program on a hardware accelerator and not the switch.
Exactly. Is there a need for such an accelerator, or you think this is actually such a lightweight language that it doesn't require any hardware acceleration?
Well, that's an interesting question. And how I understand the current state of affairs is that you keep these P4 programs lightweight enough so that your switch with their limited compute capabilities can actually process them. So like currently, these scenarios do not require us to have this kind of an offloading happening to hardware accelerators. And I believe like maybe you might need them as you try to encode more of these in-network functionalities. But then I'm also skeptical a bit that when you're doing this, you're adding an external hardware, then would you still get the line rate performance? Because these switches were like specially designed to give you line rate packet processing. How do you interface it with the delays that would incur when in the offloading process? So that's my take on this, but you never know.
Perfect.
It might happen.
Thank you so much. Thank you.
Yeah, for the hardware accelerator question, the language evolved with these hardware accelerators, or like the switch is a hardware accelerator. There's lots of these things around. I just wanted to ask if you have thoughts about making the type system fancier, like making it more precise, or any directions like that. Yeah, thanks. Great talk.
That's a way interesting question, and certainly it's a thing this work could be extended towards, because currently some of the language constructs, like the tables, which actually depend on these runtime table entries, the way we deal with them is a bit conservatively, because we're trying to do this statically. So like we conservatively analyze what the entries might look like, or like their labels. But there certainly is scope to sort of relax these constraints around like the interaction with the control plane that's trying to populate and affect or like program your P4 program itself. And also if we extend it to more of like the stateful features P4 language provides, which we currently do not do it can lead to catching information leak between packets. So like packet A's information flowed into packet B's fields. Those kind of things would also benefit by enriching the type system, certainly.
All right, so let's thanks the speaker again. Thanks for the great talk.